Namaskar, welcome back. So, this was the last slide. We're talking about the 2D image and the importance also, and why we should use the older satellite data also. Now, there is another important data which one can use. This is again available in free domain, but the resolution is a bit low. It is around like 30 meters, and this is SRTM data, Settled Radar Topographic Mission data. But now, slowly as the science advanced and the airborne data has been collected, so people have started using even the UAV data. But for generating the digital surface model or digital elevation model, and this is vegetation free digital elevation model. So you can use surface model, you can use digital elevation model, but for identifying the deformed landforms and the faults, active faults, displacing the younger landforms, mostly we suggest to use the DMs, okay, digital elevation models. Of course, this is 30-meter resolution, but then also to some extent it helps us in delineating or identifying the landforms which are formed or developed because of the tectonic movements in the past. Other than that, as we have been talking about that from the regional scale you go to the local scale. So this we can say that at least for Northwest Himalaya, this is on the local scale, which is covering area more than 200 kilometers, okay, along the strike of the Himalayan front. So this is your Indo-Gangetic plain, and this is your Himalayas, okay. So you have, and this one is what we have marked Himalayan frontal fault or Himalayan frontal thrust, okay. So this is your plate boundary, okay, present day plate boundary between Indian and the Eurasian plate, okay, because this side is the Eurasian plate. And this is your Indo-Gangetic plain, that is your Indian plate, okay. Now, coming to the site of interest, or we can say the site scale, then you can use this is the SRTM data which has been used on the right hand side. What you see is the DM from SRTM data, okay, which gives you some idea of the topographic variations and even the flat surfaces which are displaced, okay. So where you see the black lines are all active faults which have been marked, okay. And in particularly in this part, for example, if you see, then there is a clear cut shot of a discontinuity of the surfaces, okay. So this is the same surface which has been displaced by the faulting a number of times whenever there is an earthquake. And based on that, what you do is that you prepare a geomorphic map. And since this geomorphic map also includes the landforms or the features which talks about the active flexuring, okay, then active folding, strike slip faults, active thrust faults, okay, infer thrust faults and all that, okay. And the landforms here, what we call triangular facet, this we will learn when we are talking about the tectonic geomorphology part. So then this map we can call as an tectono-geomorphic map, okay, because it includes the tectonic features also in this. So such kind of detailed maps which talks about the landforms, or which shows us the landforms and active faults traces, okay. So you see an active fault trace here, So such maps are essential to be prepared before you head for your field work. Okay. So this is the first step you should do. Okay. So the type of data what we are using, this is this one is the another one which we were talking about, that you use DMs, okay, and you use high resolution satellite data. Okay. You can also play with the data. Again, this is an 3D perspective view you can see of SRTM, and you can, using any particular software, you can also generate a sort of a movie. Right now this is not, we don't have that file, but maybe in the next lecture we'll try to put that. Okay. So clearly we can see that there is a very clear cut demarcation for here about the topography, and that is your Himalayan frontal thrust and all that. Okay. And then you have over here there is an sort of an discontinuity of the landforms. There was another fault which runs over here, okay, along the range front, and this is your Shivalix. Or we also call this in sub-Himalaya. Then this one was Dune or Intermountain Valley, and then you have you have the lower lesser Himalayan rocks, okay, you can say. And there's another fault which runs over here, which is an strike slip fault. Okay. So these are all thrust faults. These are all thrust faults we are having. Okay. And this one is the strike slip fault. Anyway, coming to this, like you can also use the Landsat data. So what we did was that to generate different type of illustrations which are easy for the reader as well as for us to identify the landforms and locate the area and see the area in 3D view. Then what we did was we used SRTM, that is a DM generated by SRTM data, and then we draped over it was the Landsat. So this is Landsat data we draped on the SRTM data. Also, you can use the high resolution data and try to see and prepare your illustrations. Okay. Now coming to the part which is like we were talking about the stereo vision. Stereo vision. So this will give you to allow you to view the terrain in 3 dimension. Okay. Now I also mentioned that to get this you need to have 2 photographs taken by 2 different cameras. That is, one is the forward and another is after camera. Okay. So if these 2 cameras are having we have the photographs from these 2 cameras, 2 different photographs of the same area, you can view the terrain in 3 dimensions. So this is a typical conventional technique which we used way back in like 20 years back, and still we use. Okay, it's a part of the photogeology, or you can say remote sensing. So analysis of the high resolution satellite data, Landsat, you can use aerial photographs, you can use satellite photos, satellite imageries, low angle aerial oblique photos also you can use, that you can fly the aircraft and take the photographs. But this one which has been shown here is your stereo photograph. Okay. So if you have a portable stereoscope, we'll try to bring in the next lecture and try to show you that what sort of a stereoscope we have. Okay. So pocket stereoscope also you can use, and you can place it on this. You will be able to see the 3 dimension terrain. Okay. The terrain in 3 dimension mainly. So I don't know how many of you have played with the toys which were been available in melas, when you go and you can buy like what you used to call Durbin, and then you see the images in 3 dimension. Okay, so those like pictures where 2 pictures were been taken and they will be placed, the films will be there, and that you will be able to see in 3D. Same technique has been used here, and then that helps us in identifying the different landforms. Okay, so this we used way back, almost like 20 years back we were using, but now as the things have evolved, we have started using the we have moved mainly on the digital platform. Even if a person is having good practice, okay, they can view this photograph, 2 photographs, and generate 3D with the naked eye. Okay. Again, there is another view of the area close to Chandigarh. Now, 2D images, if we talk about, then we have like this is from Pinjore Dune, where it is bit difficult to identify, but since we know that the fault passes through this portion, okay, we can easily make out and put the lines. Okay, that is the fault trace. But for a person who is not having that idea and doing for the first time, it is going to be difficult to identify the fault. Okay, now here in this image, it is absolutely not possible to identify the fault, but one thing which you can pick up is that this portion of the photograph is showing the area which is highly dissected. Okay, so this one is highly dissected as compared to this one. Okay, so if you say this surface 1, okay, as compared to surface 2, and similarly this is also, you can classify this in surface 2. Okay, this is not much dissected. Okay, so immediately what we usually take as a thumb rule in geomorphology, that the landform which is more dissected will be an older landform, because it has remained exposed to the erosion for the longer period. Okay, so this is older, this is younger. This is one very fundamental part which we can take into consideration. Okay, and this, because this area which has been marked here is all hilly areas. Okay, so these are your hills. Okay, hill ranges, and similarly over here also these are your hill ranges, and this is what we call the alluvial plain region. Okay, now in this, if I mark right now, then you have multiple faults which is crossing this area. Okay, now, so these are the rivers which are flowing in this area, and this is not very far from Chandigarh, and this area is known as Pinjore Dune actually. And Pinjore Dune, since you have hills here, you can mark it here. Okay, so these are hills, and this you are also having hills. Okay, and in between you are having the alluvial plain. Okay, so this Pinjore Dune is nothing but intermountain valley, and this intermountain valleys, or in local language, is termed as dune. So we have Dehradun, we have Son Dune, we have Pinjore Dune, similar like that. Okay, now if you look at here, then this is your Mughal garden. I'll come to this story also. And then faults are running somewhere like this. Okay, so these are all displaced young surfaces which were displaced by along the fault by earthquakes in the past. Okay, but in In normal conditions, using this 2D image, you will not be able to pinpoint that there is a change in the elevation. Now, if you like, I put some information here, then this side is up, this is down, okay, in terms of the elevation. This portion of the Pinchor Dun is up, this is down. Similarly, this is up, this is down. And here also, this portion is up, this is down. And same goes over here, up, down, okay. And this place also, this is up, this is down. So fault is somewhere running like this, okay, over here. It goes like this. And in Pinjore garden area, the fault runs like this. Okay. So in 2D, you won't be able to identify this. Okay. So if I take the cross section, for example, at any location over here, for example, this, if I taking A and B, then that you will be able to see something like this topographic variation. So this change in the elevation, okay, is because of tectonic movement, and this you won't be able to identify with the 2D images. Okay. Anyway, coming to this, for example, if you see the field photograph of this one, as I told that this side is up and this is down. Okay. And the photograph which has been taken is like viewing this side. Okay. So we were standing somewhere in this area, and then we have taken the photographs, and which looks like this. Okay. So fault runs over here. Okay. And this area is like topography is this. Okay. So the front part, where I have put the arrow, is this one. And this has a slope which is towards, like we can say, northeast. Okay. So this is the back tilt. Okay. We see this type of landforms as in back tilting. So fault section, or we can say, will be somewhere over here actually. Then if you see this one, again, as I told that this is up and this side is down. Okay. So this is photograph has been taken from this side, viewing the uplifted part or the upper part. So this is the up portion and this is the down portion. And this is inside the garden. Okay. So fault runs over here. Now this garden was been constructed way back in 17th century by Mughals. Okay. Now till since then there is no earthquake recorded on this fault. Okay. There was an earthquake in 1400 AD. So 1400 AD was probably the last event on this. Okay. That means more or less like we can say in 15th century. And this was when constructed in 17th century. Okay. That is around 1600 AD. So after this earthquake. Okay. And just outside, that is, if you look at this area, the photograph has been taken from here. This area, there is a small road which goes. Okay. And that area shows this elevation change. Okay. So this side is up. The person standing here, you can see this side is up, this is down. Okay. Now active fault traces, we also, as I told that we use the aerial photographs. Okay. So what we did was, this is after 2001 Bhuj earthquake. We again, because at that time almost like more than 20 years now. Okay. So this was in the earthquake was in 2001. named as Bhuj earthquake, and magnitude was 7.6 or maybe 7.8 if I'm not wrong. Okay. So what we did, we used corona photographs, corona satellite photos, as well as we also did aerial photography. Okay, as I was mentioning that you can have low oblique photographs. Okay, so this is the oblique photographs which we have taken using the aircraft, and aircraft was we flew in this direction. Okay, and viewed the terrain like that. Okay, so what you see here in the aerial photograph, which has been oblique photograph. Okay, but it is not very, like, we don't see the horizon here, but then also there's an oblique one. So this portion which you see here, okay, this ridge lines, okay, this one, this ridge line is nothing but this one here, this ridge lines. Okay, so these are the two ridge lines which you can see, and this is the fan area which we identified, and then we identified that there is a fault which runs over here. Okay, and this is what our identification is. Okay, so this is an active fault trace. So this was the first time we identified the active fault in Kutch. Unfortunately or fortunately, this fault did not move during 2001 Bhuj earthquake. So a direct implication is that it will move in near future. Still, the potential is there in this area, okay, to trigger large magnitude earthquakes. Okay. Then another part was this Jawahar Nagar, okay, this area where we were able to identify, but still this part is over here only, not very far. So this one is, if I'm not wrong, this area is this one actually, Lodai area. So we see a very clear cut sort of an discontinuity of the flat surface, that is your alluvial fan surface, and this portion towards the north is your what we call the Bunny plains. Okay, and this a portion is sitting over here, this region, and the boundary of the hills you see is this one here actually. So again, the photograph was been taken looking this side. Okay, and this side is your north and this is your south. So photographs were taken looking south. Okay, another photograph finally is from Jawahar Nagar, this area, okay, where we can see clear demarcation of your or discontinuation of the fan surface. Okay, so this discontinuation is nothing. This is alluvial fan surface and this is Bunny plain. So this is an active fault trace. Okay, so what we learn here is that we can use satellite data, we can use even the aerial photographs, we can use digital elevation models or digital surface models using the SRTM or any data which has been generated, or even the stereo photographs can generate your digital surface models. Okay, and if you are having LIDAR, then that you can use as an digital elevation model. Now coming to the finally the low sun angle aerial oblique photographs, as I was talking about in what we did in Kutch. This is the photograph from US, and the trace here what you see is of your San Andreas fault system. So such techniques can be used to first identify the sites to understand the pattern and the distribution of the fault, and then you can go into the field finally and start for the paleoseismic studies. Okay. So with this, we'll stop here and continue with more discussion on the field mapping of an active fault studies and paleoseismic studies in the next lecture. Thank you so much. Namaskar.